Hello everyone. Today we're looking at the problem Design Task Manager, which was question 2 in Biweekly contest 147. We don't often get these kind of design questions in contests. This is a pretty cool one to work through. Definitely a little tricky unless you know a certain trick and how to apply it. So the question reads that there is a task management system that allows users to manage their tasks, each associated with a priority. So the system should efficiently handle adding, modifying, executing, and removing tasks. So then we get the outline of the task manager class that we actually have to implement. So the constructor is just going to get a list of tasks in the format of user ID, task ID, and priority. We also get to implement the add function, which basically will take in a user ID, a task ID, and a priority, and then we have to add that task into our task manager. And it's guaranteed that a task with this ID will not exist in the system at this point. There's also the edit function, which will update the priority of an existing task ID to the new priority passed in, and it's guaranteed that this task will exist in the system. There's also remove, and that will remove a given task ID from the system. It is guaranteed that this task will exist. And then finally, our execute top, which is kind of the main purpose of the task manager, where essentially we will take the task with the highest priority and we will execute it. If there is a tie for highest priority, we will execute the one with the highest task ID. And then whatever task we choose to execute, we will return the user ID associated with that task. If there are no tasks available at any point, then we can just return -1. So this is the given input that we'll be working with. So you see this first argument is just a list of tasks that we are going to input. So we have 101, 102, 103. Then our second is we're going to add this task in. So we're going to add this task for 104. Then we're going to edit task 102 to have a priority of 8. Then this empty will represent executing whatever task is at the top. Then we're going to remove 101, add 105, and again execute. So our output would look like this. These nulls are for all the instantialization, add and edit, and remove. And then we'll see the first time we execute, it will be a task for the user ID 3, and then secondly, a task for a user ID 5. So you may be thinking, since we're dealing with priorities, we should use a priority queue, and that is a very good instinct. So we're going to initialize the tasks that were given off the bat in a priority queue. So after our first step, our priority queue would look something like this. So we could use a max heap for this. So essentially what will happen is that the maximum priority as well as the task ID will be towards the top, right? So we're always going to be able to access in constant time whichever task has the highest priority as well as the highest task ID. So we'll see here that we have task 102 at the top and then these other ones below it. And it doesn't matter their order. All we care about is whatever is at the top of our heap. So this is this first step here. Then what we're going to do is we're going to add this new task. So the task ID 104 with a priority of 5 for user 4. So we can just add that down here and just kind of go to the next spot in our heap. So we'll have a priority of 5, task ID of 104, and then a user ID of 4. So now this is done. So this is where it gets interesting, right? We want to update the task 102 to now have a priority of 8. So you'll see here that our current priority is 20. But we want to now make this 8. So in this case, it's pretty convenient because it's right at the top, right? But this is not always going to be this case. So it could, for example, be all the way down here. We could have that task. So what we'd have to do is we have to essentially search the entire priority queue to find this and then update that element there. So we could do this, but it's not going to be very efficient. So here is the first example of kind of where our priority queue alone breaks down. But anyway, let's say we did it that way. We searched through our entire priority queue. We found that task and we updated it, even though it is very inefficient and honestly not very easy to do. So we consider this to be done. Then we remove the top. So we can just take whatever is at the top and we can remove that for now. So we will do that. So now we removed that top and we returned the user ID, which was 3. So now the next step is we want to remove 101, right? So again, here it's convenient because 101 is at the top, but we don't always know that. That won't always be the case. So again, we have to search through this entire priority queue, which again is going to be inefficient, it's going to take a long time, and it's not going to be easy to implement. So we could do that and remove this. So now we want to add this new task here, task 105 with a priority of 15. So that would go at the top of our heap up here. We could do 15, 105, user would be 5. So that would be at the top. And then again, at the end, we would process the top, and then we would return this 5 essentially. So you kind of see that a priority queue works for most of the time, but for editing and removing, it can become very tricky because we have to essentially search the entire priority queue, which is going to be very costly and also not very easy to implement. So if we add something else into our processing, we can make this a little bit easier. So for this solution, we're still going to use our priority queue, but we're also going to use a hash map. And what this hash map will do is it will track the current state of each task. And you will see what this means as we go forward and why we use this. But essentially, we're going to have a hash map where we have the task, which points to the current priority, as well as the user, right? So we're going to use this in order to keep track of the tasks as we go through, and you'll see how this is helpful. So to start, I'm going to have this hash map just have all the initial tasks that were passed in, each of their task IDs pointing to their priority as well as their user ID. So let's see what happens as we go forward. So we've done this, then we're going to do this add step here. So we're going to add this task in, we can just add it over here, priority of 5, we're going to have the task ID 104 and the user being 4. I'm also going to add this into my hash map here, so I'll have 104, priority of 5, user 4. So easy enough, nothing really changed. So then we get to the edit step, and this is where you can kind of see what we're going to do and how we use the hash map. So now what we're going to do is we're going to update this state. And remember, this is going to keep track of the current state of each task, right? So what we're going to do is we're going to update this priority here to be whatever we are now given. Now you see that my priority for 102 is 8, and then I'm also going to add in a new entry into my heap with a priority of 8 for 102 and then a user of 2. So now you'll see something interesting. I actually have 2 entries, right, for this task. I have one with the original priority and then one with the new priority. And this is okay. You're going to see exactly how we handle this conflict. So now we want to remove the top. And we know from our previous iteration that this is going to be user 3. But as you could see, right, at the top of our heap, currently we have user 2 with priority of 20. But now we're going to use our hash map. So we come down here, we see, all right, this is our top task. Let's check in our hash map. So we'll see here that the current task 102 actually has a priority of 8. So we've updated it to 8. So that means that what we see here is actually outdated, right? This represents a previous state of task 102, but not our current state. So we're going to take our task at the top and we're going to check in our hash map and we'll say, does the user match? It does. Does the priority match? It does not. So this means that this is not valid. This is out of date and that's actually a valid task that we want to consider right now. So then we're going to continue past this. Then this would be our next task in the heap and we'll say, let's do the same thing. Let's check out task 103. This is valid. Priorities match, user match. So this will be the one actually that we're going to execute and we're going to return that user ID 3. So we finish this. Next, we're going to remove 101 from our heap. And you'll see here that in our previous example, 101 was at the top, but here it's not. So do we have to go through the entire priority queue and figure out where it is? Well, no. So what we're going to do is we're going to delete this from our state, right? We're basically going to say, so this task has been deleted. I'm not going to consider it anymore. So then what's going to happen is later on, if I'm executing tasks and I see a task 101, I'm going to say, all right, well, I'm looking at task 101, but I see that's been removed from my state. So I know that this is not a task I want to process because even though it's in my priority queue, this current state of my task manager is telling me that 101 is no longer a part of it. So then what we could do is say, if I ever come to this, I'll look in my state. If this has been removed, then I do not want to process that task. So again, we kind of avoid having to iterate through the entire priority queue and instead rely on just our state hash map here. Next, we're going to add this new task. So this should be fairly simple. We can add this down here with 15, a task of 105, and ID or user ID of 5. So again, we come to the top and we would do the same exact logic. Essentially, we would just go through the top element of our priority queue, and while it's invalid, while these don't match whatever is in there, we're just going to continue past those until we find a element in our priority queue that matches the state. So essentially, by using both a priority queue and using a hash map, we can kind of bypass having to go to the priority queue for every edit and remove operation and just rely on that hash map to tell us if an element in the priority queue is valid or not. Let's hop over to the code and see exactly how this works. So in our init, we're going to set up two things. So this is going to be our hash map, which represents the current state of our tasks as well as our priority queue. Just to note, I'm using a min heap here, even though in the explanation we use a max heap. This is just because the heap queue library in Python is implemented as a min heap, and to make it a max heap, we're just going to use negative values. So don't get confused. You can just follow the max heap logic if you have one in your language, but for Python, this is kind of just a workaround of using a min heap. So we're going to take all our tasks and we're going to, in our hash map, we're going to say each task ID is the key, and then we're going to point to the priority and the user. And then into our hash map, we're going to push this tuple of priority, task, and user. For add, very simple. We're just going to add that task into our hash map and then also push it onto our heap. So then for editing, what we're going to do is we're going to get the current user ID that we currently have in our hash map. And remember, we are guaranteed to have this task whenever we have an edit operation. So we're going to update this task with the new priority we're given, as well as the previous user ID that we had. Because remember, we're just changing the priority, we're not changing the user. Then we're going to push that onto our heap. Remove, very simple, we're just going to remove that from our hash map. So here's where things get interesting. So execute top. So what we're going to do is while we have elements in our heap, we're going to pop them off. And here is just kind of working with the Python heap queue library. I'm taking those negative values that I used to force the heap to be a max heap and just converting them into positive values. So basically what I'm saying is that if the task is not there, meaning that we've deleted the task previously, or if the priority doesn't match what we have, or the user ID doesn't match what we have, we're going to continue past that task, right? So this means that this task is not valid and I do not want to process it. So I'll keep popping elements from my heap and keep looking until I find a task that is valid. However, if I do find a valid one, I'm going to remove that from the hash map because I've processed the task, it's no longer there, and then return the user ID. And then this is the case down here where we go through our entire heap and don't find any tasks that we can process. So here we just return -1. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.